Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover a very common proof that you'll see in linear algebra and actually through a lot of grad school as well. So it says, if U and W are both subspaces of vector space V, then their intersection, U intersect W, is also a subspace of V. And what I've done is I've drawn a picture here. So what I know is that V is a vector space. Now, since V is a vector space that has all 10 properties of a vector space, really the main two properties we're going to talk about subspaces is going to be closure under vector addition and then also scalar multiplication. So that's what it says U is. U is a subspace of V, so I know U has those two properties. As I said, it's closed under vector addition and scalar multiplication. Same thing with W. W is also closed under vector addition and scalar multiplication. So what I want to prove is that their intersection itself would be closed under a vector addition and scalar multiplication. Now let's kind of talk about what that means, like what it means to be closed. Let's go after U real fast and just kind of verify that. So what it means is if I have, like, say, a U1 in here and I have a U2 also in here, and let's say these things are vectors, I'm just doing it as dots. Let's say those are two vectors. Then what I know is that that other vector, that U1 plus U2, will also be in that vector space, guaranteed. Because what it says is if, U is a subspace of V, then I can say that there is a U1 and U2 in U. So these vectors are in U such that U1 plus U2 is also going to be in U. And that's what I've drawn here. Also, I know if I have any vector U, and let's say this U here, then I also know that, say, somewhere in here there's going to be some C times any vector U. So also that means CU2 will live in there as well. Any vector I can also multiply by a real number scalar C, and it'll still be in that, that general vector space U. So then I can also say that, so this means closed under scalar addition, also means that any C times U will be in U as well. Now, we also said that W is a vector space. Well, to be a subspace, it is a vector space all by itself, and really to prove something is a subspace, I just also have to show that it's closed under addition and scalar multiplication. So again, it's going to have this exact same property. I'm not going to draw another one. So, if I'm talking about, W is a subspace of vector V, then also means that, say, if there's a W1 and W2 that both exist in W, then I can say that W1 plus W2 is going to be an element of W, and I can see C times W1 is going to be an element of W. Remember, this is arbitrary. I know that C times that one also will live in there, but we're supposed to talk about the arbitrary. Now, for me to prove that their intersection is also a subspace, I have to prove these two properties. That the subspace themselves, or the intersection themselves, is also a subspace in this, in this set. So the subspace, or the thing we're talking about, is going to be this piece right here. And that right there is the intersection of, can't make it any better. So that's just what it is. So that's going to be the intersection that we're going after. So let's I guess draw it in a color that's working. So let's say this green right here. So I have to prove that that piece there is also a subspace. So I have to prove that that piece right there, has these two properties. So what I'm going to do is I'm going to let, let's just say vector V. I'll just say V1 and V2 be elements of, say, U intersect V. What I need to now prove is that these two vectors are closed, U intersect W. I need to prove that these things are closed under vector addition and scalar multiplication. Now, what does it mean to be in the intersection? What this implies is that if V is in the intersection of U and W, that means that, V1 is an element of U And I can say that V1 is an element of W. So what does it mean to be an element of this and also an element of this? Well, what I have to show is that if this is an element of W, then let me back that up. So what this implies that V1 and V2 are elements of U, and V1 and V2 are elements of W. Because I'm in their intersection. Notice that, here I'm in U, and here I'm also in W. So what I have is I have two arbitrary vectors inside here. So I can tell they're both in U and also in W. Now remember, to be in U, what that means is that U is a subspace. So that means V1 plus V2 is also going to be in U. And since this is a subspace, that also means that V1 plus V2 is also going to be in W. Now since their sum is in U and also their sum is in W, then their sum has to be in the intersection of W. So therefore, V1 plus V2 is going to be in U intersect W. Now I also have to show a closed under scalar multiplication. So I can say something very similar. If V1 and V2 are U and W, let's just go after the V1. So since V1 is an element of U intersect W, this would imply that V1 is an element of U and V1 is an element of W. I know I said it already, but I'm trying to do the argument separately. So since V1 is an element of U and U is a subspace, that means CV1 also has to be in U. Very similar, since V1 is also an element of W, then that means, remember W is a subspace, so that means it's closed under scalar multiplication as well. It means CV1 also has to be in W. Which really means that CV1 is in U and also CV1 is in W, so it's got to be in both at the same time. So therefore, CV1 is going to be an element of U intersect W. And since it's closed under scalar addition and also vector multiplication, this implies is a subspace of V. If you like the content, please subscribe.